Good morning students. Today our topic is real numbers in that assignment number 1. So first question, show that one and only one out of n plus 2 or n plus 4 is divisible by 3 where n is any positive integers. See here he is given a 3 numbers n plus 2 and n plus 4. Out of these 3 only one is divisible by 3 at a time. Alright. So consider n is any positive integers. Now we are proving, let n be any positive integer, then we are writing in the form of, write in the form of Euclid division lemma. See children, I am writing n is a positive integer, then I am writing in the form of Euclid division lemma b cube plus r, where r is the remainder. The condition for the remainder is which is 0 or greater than r less than b. See children, consider b is equal to 3. Consider b is equal to 3. So the natural number which is divisible by 3. Therefore, n is equals to 3 into q plus r. So the possibility reminders are c less than 3. So possible reminders are what are the possibility reminders? 0, 1, 2. These are the possibility reminders. These reminders are we are substituting that equation. So now case 1. Case 1. For r is equals to 0. Now you should substitute in place of r is 0. Therefore n is equals to 3q plus 0, then 3q. So which is divisible by 3? Which is divisible by 3? Divisible by 3. See in next one. Next condition is n plus 2. N plus 2. So n plus 2. What is n value? 3q. 3q plus 2. See here children, 3q plus 2 is not divisible by 3. Not divisible by 3. See, and the next one is n plus 4. So in place of n, what we are substituting? 3q. 3q plus 4. See here also which is not divisible by 4. Not divisible by 3. Divisible by 3. Now I am taking the second condition, case 2. Now I am considering a remainder is 1. So for r is equals to 1, then n is equals to, so 3q plus r. In place of r we are substituting 1. See children, it is not divisible by 3. Not divisible by 3. Now n plus 2, second n plus 2. So in place of n we are substituting 3q plus 1. So 3q plus 1 here plus 2. So 3q plus 1 plus 2 is 3. See, I am taking a 3 as common, then q plus 1. See here children, 3 is out. So now it is divisible by, yes, divisible by 3. Now in next case, n plus 4. See here children, 3q Here n value is 3q plus 1 plus 4, which is equals to 3q plus 5. Here if you observe that 3q plus 5 is not divisible by 3. Now case 3 for r is equals to 2. So now we are considering remainder as 2. Then in place of r, what we are substituting? 2. N is equals to 3q plus 2, which is not divisible by 3. Next one is n plus 2. See children, here n plus 2 means in place of n, what we are substituting? 3q plus 2 plus 2. See here, then 3q plus 4, it is also not divisible by 3. Now the next one, so n plus 4. So n plus 4 means in place of n, what we are substituting? 3q plus 2 and plus 4. Here 3q plus 2 plus 4 is 6. Take 3 as common, then q plus 2. See here children, it is divisible by, so n plus 4 is divisible by 3. So it is divisible by 3. See children, here if you consider these 3 cases, so in first case only n is divisible by 3, in second case only n plus 2 is divisible by 3, in third case is only n plus 4 is divisible by 3. In other than these 3 cases, none of them is divisible by 3. So the condition is right or not? So only one among these 3 is divisible by 3 at a same case. See children, so all above, therefore all above three cases we observe only one of either n or n plus 2 or n plus 4 is divisible by 3. Hence proved. Next question. Question number 2. Consider the numbers numbers 4 to the power of n, where n is a natural number and is a natural number, natural number. Check whether there is any value of n for which 4 to the power of n ends with the digit 0. See children, the simple what he is asking means 4 to the power of n. The power is always a natural number. He is saying that n is a natural number. See, 4 to the power of n, where we are considering n as a natural number, then any value of n, 4 to the power of n ends with a 0. See, if any number ends with a 0, means it must and should be a prime factorization in that 2 and 5 must be there, right? So while we are prime factorizing a number, there must be 2 and 5 is there. If 2 and 5 present in that number, then it is ends with a digit is 0. See children, here if you observe that 4 to the power of n, for the number for the number 4 to the power of n to end with the digit 0 for a natural number, n, it should be divisible by 2 and 5. Should be divisible by 2 and 5. See children, it is divisible by 2 and 5 means what it is, in the prime factorization there must be a 2 and 5 presence is there. Should be divisible by 2 and 5. This means that the prime factorization of 4 to the power of n should contain two and 5, but it is not possible. See children, why it is not possible means the prime factorization of 4 to the power of n. See children, here prime factorization 4 to the power of n. See children, here it can be written as 2 into 2 whole to the power of n. It means we can write it as 2 to the power of 2n. 2 to the power of 2n. See, here 2 is the only prime factor. Here the 2 is the only prime factor. It is not there. 5 is not there. 5 is not there. So 2 is Therefore 2 is the only prime in the factorization. 2 is the only prime in the factorization since 5 is not present in the prime factorization. 5 is not present in the prime factorization. Therefore, there is no natural number n. There is no natural number n for which 4 to the power of n never end with the last digit is 0. Why it is not end with the 0? In the prime factorization, 5 is not present in the prime factorization. That's why it is not never ends with the last digit is 0. Now the next question. Question number 3. Find the LCM and HCF. Find the LCM and HCF of the following integers. Following integers by the prime factorization method. By the prime factorization. Prime factorization. See children, what are the numbers given? 12, 15 and 21. See children, by using prime factorization method, given numbers are 12, 15 and 21. Prime factorization of 12 is, so 12 is prime factorization of, so we should be write 12 as a product of primes, that is 2 into 2, 4, 4, 3 is 12. It can be written as 2 square into 3, 2 to the power 2 into 3 to the power of 1. And the next one is, see children, of 15. 15 we can write it as 3 5s are 15. It means 3 to the power of 1 into 5 to the power of 1. And next one is 21. 21 we can write it as 3 into 7. So 3 to the power of 1 into 7 to the power of 1. See children here, what he is asking. He is asking about LCM. LCM of 12, 15 and 21. See, what is LCM in prime factorization? We should take all the prime factors with highest powers. We should take all the prime factors with highest powers. So what are all the prime factors? 2, 3, 5, 7. What are the highest factors? So 2 having a power is 2 is the highest one. 3 is 1, 1, 1. So see children here. So 2 square into 3 into 5 into 7 is how much? 420. And HCF of 12, 15, 21 is, see children here. Now HCF means highest common factor. We should consider among these a common factor. What is the common factor? 3 is the only common factor among these 3 numbers. So 3 is the HCF with least power, right? So only one has the power. Then this is the HCF. HCF of 12, 15 and 21 is 3. Question number 4. What is the last digit of 6 to the power of 100? So he is asking about what is the last digit. It means a unit place digit of 6 to the power of 100. So we know that, see children here, we know that 6 to the power of 1 value is 6. 6 square value is 36. 6 cube value is 216. 6 to the power of 4 value is 496, and 6 to the power of 5 value is 7776. If you see, if you go with take all the positive powers, then if you observe that the last digits of the results, so 6 to the power 1 is 6, 6 square unit digit is 6, 6 cube unit digit is 6 to the power of 4, unit digit is 6, and 6 to the power of 5 unit digit is 6. Then if you continue this, and 6 to the power of pn, the last digit is 6 for n is a positive integer. See children, you should take any positive integer as a power of 6, then the last digit always 6. So we see that, therefore we see that 6 to the power of n for any positive integer and ends with 6. Therefore, unit place of unit place of 6 to the power of 1 n is 6. Therefore, last digit in the sense unit place digit, last digit of 6 to the power of 100 is 6. Last question. Question number 5. How will you show that? How will you show that 17 into 11 into 2 plus 17 into 11 into 5, right, is a composite number, is a composite number, is a composite number. He is asking to show that. See children, he is asking to show that this expression 17 into 11 into 2 plus 17 into 11 into 5 is a composite number. So show that this number is a composite number, that expression. So now the solution. Given expression is into 11 into 2 plus 17 into 11 plus 5. See children, here in these two terms take 17 into 11 as common, then 17 into 11 into, see here what is remaining here, 2 a plus a 5. See here 17 into 11 into 2 plus 5 is 7. See children, the whole expression is, we are writing as a product of three numbers. As a product of three numbers. As a product of three numbers means these three numbers are factors of this number. These three numbers are factors of this number or not. See children, what is composite number? Other than two factors. Other than two factors. What are the two factors here? 1 and itself. So 1 and itself, other than two factors. See children, it means only 5 factors totally. So it is a composite number or not? It is composite number, right? So we are writing as a product of three numbers, then it is a composite number. See children, now the given expression is written as product of three numbers. Product of three numbers, right, and hence it is a composite number. It is a composite number. Thank you students.